Hello, and welcome to the Introduction to L Networks. For those following along with the lab, this is for Lab 5. So what is an L network? An L network is a matching network that uses a shunt and a series component, and it can match a complex impedance to your characteristic impedance with some combination of inductors and or capacitors. It provides a simple and effective matching network, using only two elements, of course, and it creates a compact design at lower frequencies where wavelength dependent designs could become prohibitively large. The one downside is they do tend to be narrow banded thanks to the frequency dependence of the impedance of inductors and capacitors. So there's two different configurations that you have to remember for an L network. And you'll see that they are in a L shape, which is where they get their name. You can have a series and a shunt, or a shunt and a series. What makes the difference is whether your load impedance is greater than your source characteristic impedance, or the other way around, where your load impedance is less than. If you want a way to remember, you can always remember the L network points. If you look at where it points over towards the larger value. With any matching problem using the Smith chart, I like to think of it as a treasure hunt, where our goal is to hit the center, which is matched. But that also means that if we ever hit the r equals 1 circle, we are only one lumped component away from a matched network. Also, if we ever hit the g equals 1 circle, all we have to do is flip, and then we are one element away from a matched network. So when doing a matching problem, either one of these can be our target to approach a better match. So let's look at this in practice. For the case where the characteristic impedance is greater than our load impedance, for example, if I pick 0.5 minus j as our load impedance, you can see that all we have to do is move up until we impact our g equals 1 circle. And so all I have to do here is add 0.5j, and then I'm on my g equals 1 circle. And now all we have to do is a simple flip into admittance, and then by subtracting j from that admittance value, we are at a matched point. So let's look at what we did as a circuit, right? Starting at the load, we added a series impedance and then flipped to admittance. So now we add a shunt component to subtract that j from the impedance value and get our characteristic impedance. So we have a positive impedance and a negative admittance. So this would be analogous to an inductor and in series, and then an inductor in parallel. The astute among you might realize that I could have continued up this circle and added a much larger value. So then when I flipped, I had a positive admittance that I added, and that would have given me an inductor then a capacitor. Whenever designing an L network, you'll find that you can have two different solutions, and it could be advantageous to explore both, as sometimes you will get more realistic component values out of one than the other, or component values that better match the ones that you have on hand. Let's look at the case where the characteristic impedance is less than the load impedance. For this example, I'll select 2 minus j. Now you'll notice that unlike the previous example, I can't simply add or subtract an impedance. I'm stuck on this circle here and no way to approach the r equals 1 or g equals 1 circle. So first we have to flip to admittance to escape the circle, and now we can add or subtract a value from our current position and intersect our g equals 1 circle. I will choose to subtract 0.69j and intersect the g equals 1 circle at about 0.4 minus 0.49j. Now that we are at our g equals 1 circle, all we have to do is flip once more back into impedance, and we have our current position of 1 plus 1.22j. All we have to do is subtract out 1.22, And now we are once again matched. So let's look at our circuit and see what we did there. Remember, first we flipped into admittance, and then we added what will be a shunt component. Then we flipped back into impedance, so we added a series component. To wrap everything up, we've seen that L networks can match complex impedances to our characteristic impedance. They only require two elements, which makes them a simple and often compact design, and they're commonly used throughout industry in design with amplifiers or antenna matching.